In this demonstration, we're going to see how you can tune an abstract model to match the simulation results of a more detailed model. We have a model of a dual clutch transmission. The detailed variant of the dual clutch transmission includes all of the gears and the dog clutches that control the pre-selection of the gears. Our abstracted version of the transmission simply consists of a variable ratio transmission, and the same control system is used to simply select the gear ratio for the transmission. However, when we test these two variants, we can see that the abstract variant does not match the simulation results of the detailed variant. We could tune the parameters in our abstracted variant by hand, but a more efficient way to do this is to use Simulink design optimization to automatically tune these abstracted model parameters. Our abstracted model has two parameters that we wish to tune: a delay and a ratio time constant, or a filter that is used to control the changing of this gear ratio. By allowing Simulink design optimization to automatically tune these parameters, we can get a much better match between the detailed and abstracted models. I'll now switch over to the model so that you can see how this is done. Here is the model that we're working with. We have an abstracted model of a dual clutch transmission. We can see from this scope on the simulation results, the pink line are the simulation results from the detailed model, and the yellow line are the simulation results from the abstracted model. These results don't match. If we look at the abstracted model of the dual clutch transmission, we can see that there are two parameters that we can tune. We have a MATLAB variable that controls the delay of the changing of the gear ratio, and we have another MATLAB parameter that controls the time constant on a filter for the changing of the gear ratio. We could try to tune these two parameters by hand, but a more efficient way is to use optimization algorithms to tune that parameter. Here we're going to start Simulink design optimization to tune these two parameters automatically. You can see in this graphical user interface that we have specified the detailed the response that we want the simulation results to track. This is from the detailed simulation. The colored lines that you see overlaid here are intermediate results during the optimization process. Each time you see the scope blink, Simulink design optimization has rerun the simulation with a new set of parameter values. It checks to see how far away it is from the desired response, and then based on the sensitivity of the parameters, readjusts those values and runs the simulation again. We can set up this optimization to use any of a number of optimization algorithms, and we even have the option of running these simulations in parallel. Simulink design optimization will continue tuning these parameters until the results of the cost function, or the difference between the two signals, lies below a tolerance that we have set. We can see that the optimization has already run over 30 simulations, and the results look a lot better than they did in the very beginning. When the difference between the two functions lies below the tolerances we have set, the simulations will stop running, and we'll see the final values over here in this window. At this point, the lines are quite close to one another. And this is going a lot faster than it would go if I were to do this by hand, and the results will be certainly much more accurate. So at this point, we've run almost 50 Simulink design optimization has run almost 50 simulations. And we can see that it has found a set of results that minimize the difference between these two plots. So we have used the results from the detailed simulation to tune parameters in the abstracted model in order to make sure that we can use this abstracted version, gaining simulation speed without sacrificing too much accuracy. This demonstration has shown how we can use optimization algorithms to tune abstracted models.